All right, as we get our next presenters up here, I wanted to make one note. So many of you have enjoyed seeing all the student posters. They're still on display. Some of them, a couple of them had to leave, and so they took their posters with them, as they should. But during the networking break coming up after this talk, feel free to go in and take another look at those posters. It's amazing stuff, and we will be presenting the winners of the poster contest today right before our luncheon speaker. Great accomplishments by all for that. So, clicker, there you go. Thank you, absolutely. Okay, so speaking of radiation, so NASA Glenn is developing new radiation detectors based on wide band gap semiconductors to meet the challenges of low power, low noise, multidirectional, robust detectors for a wide range of particle mass and energies. So with us today, we have Susan Rabanek, who works in the optics and photonics branch in the research and engineering. No? No? Sorry, bad bio.
We're both in the same branch.
Oh, okay, gotcha. Well, why don't I do this? I'll let you guys introduce yourselves. How about that? Just so it's accurate. All right, so take it away. Thank you.
Okay, hi, I'm John Werbanek. I'm in the Smart Sensing and Electronics Systems branch at NASA Glenn Research Center. And do you want to introduce yourself?
I'm Susan. Morning. I'm Susan Werbanek, and I'm also a member of the Smart Sensors and Electronics Systems branch.
Okay, so we're going to talk to you about what we've been doing for the advanced radiation detectors and detector systems that Jim referred to. So the outline is that we're going to tag team this. I will start off talking about the challenges that we're addressing, the systems that our branch works on, the radiation detector research that we work on, the benefits of going with wide bandgap detectors, our future concept, and then Susan's going to take over and talk about the systems that we've been working on, specifically detectors, and LET detectors and the Envision applications for deep space CubeSats, lunar prospecting, and fission surface power. So as we've been seeing, that knowing the radiation environment real time during these missions is vital for deep space missions, and several places have called out specific priorities to address gaps in the technologies. Space weather is a big one. The highest priorities are for multi-point particle and field measurements and radially distributed particle and field measurements. For STMD outlined several gaps, shortfalls in their technology framework, and from advanced instrumentation for radiation modeling, extreme multifunctional instruments, reducing the instrument size, mass power. You need situational awareness for lunar environment when you're doing lunar operations. And then just for heliophysics again, you need field and particle detectors. This is sort of summarized a common theme that was brought out in the 2012 technology roadmap, is that robust sensors capable of operating for long periods in environment of space are needed to measure radiation at the destination as well as during the journey. Other studies have pointed out that when you're talking about space weather, nowcasting and forecasting, the capabilities right now are limited to essentially this side of the sun. So if you want extended missions, you need varied location to respond in a timely manner to changes in environment, because the space weather, the solar wind comes out from the sun not linearly. It spirals around, it swirls. You get some interesting space weather effects. One of the some of the things that were outlined in the technology roadmap, the 2012 roadmap, is what enables these type of measurements. Integrated multifunctional sensor detector technologies, rad-hardened electronics, and compact systems for smaller platforms. Fortunately, the Smart Sensing Electronic Systems branch, we work on that. We're a interdisciplinary group made up of chemists, physicists, electrical engineers, material scientists. We work on developing instrumentations to handle measurements in difficult to measure environments, often high temperature, often harsh environments, variety of areas, silicon carbide based electronics, MEMS systems, pressure, acceleration, sensors, chemical gas species, microfabricated thin film sensors. Radiation sensors sort of fall in that category, and harsh environment nanotechnology. We do this research in-house. Okay, we have microfabrication facilities in-house to produce all our own sensors and all our own electronics. And you can see a picture of inside of the clean room and some of the devices that come out of our research that we do there. So we're leveraging these capabilities as a space radiation instrumentation research. We've dabbled in some of this stuff in terms of that we've tested silicon carbide JFETs on MISSI on the station exposure, and we've worked on series. This is a cloud reflection stuff, reflecting light project. But we want to address the issues for embedding instrumentation, making precision instrumentation, and compact instrumentation. And this is where we start getting into the wide bandgap areas. So when you start shrinking the size and you want to start reducing the power, you need to use the wide bandgap to enable these applications. Here, the pictures, the graphics that we have on here are some of the technologies that we've been working on, which we will talk about a little bit later. But the applications are from deep space CubeSats to ISRU to fission surface power. Why wide bandgap? Wide bandgap semiconductors means that the energy gap between your conduction and valence bands are wider than that of silicon. That makes them inherently thermally stable. That makes them inherently radiation tolerant. It also means that they're very low power. They're very low current. So here are some of the properties that we've measured on some of our devices compared to what you can buy commercially state-of-the-art is outlined here. So some of these detectors, an LET detector, a linear energy transfer detector, we've seen increases or the dark current is significantly less than what you find commercially. We've looked at gallium phosphide as for a scintillator, coincidence and coincidence detectors. Here again, the current is much lower than you would get for commercial detectors. And we were looking at a Cherenkov detector, which based on zinc oxide instead of what you would get for a PMT. So that not only reduces the size, it reduces the power as well. Okay, so we've got these wide bandgap technologies. We can put them together as our concept. What is the maximum benefit you can get to this? If we put all these technologies together, what you can enable is a multidirectional compact full field ion detector system, or CFID as has been referred to as. So this you can map heavy ions for a wide range of energies, being rad hard, rad tolerant, and thermally stable. You can start talking about 10+ year missions, and this is compact. You can see the ruler on this render. This would fit in a CubeSat, right? This is small, and these are the detectors. And we've got some patents that covered this technology. Here's a cross-section of a wedge of the CFIDs. So this is like one direction where you have layers of the linear energy transfer detectors shielding to define the field of view using coincidence anti-coincidence detectors, and in the center to capture the high energy signals, a Cherenkov detector. And there are technologies that we've been developing to work on to enable this to happen. And with that, I will pass it off to Susan so she can talk about some of these technologies.
Okay, continuing what we've been working on. John showed you the concept. In fact, let me back up a couple of slides here. The compact full field ion detector system and the cutaway of how it would work with the different detectors stacks around the central Cherenkov detector. And that lets us try to get a wider variety of space radiation in a single package in a smaller space. And so, but it doesn't have to be implemented as the entire sphere. If someone doesn't have the need for or not the space for the entire thing, each of those separate components could be implemented as an individual module. And so the linear energy transfer detectors, the silicon carbide linear energy transfer detectors could be used singly or as a stack, or as a stack with insulation between layers if you want to do some particle sorting. Scintillator detector systems can be used in a variety of ways also. And this shows some of the data from some of our earliest work. On your left there, the graph at the bottom shows a commercial silicon carbide sensor that we just tested with some alpha sources that we have at Glenn Research Center. And it shows the little humps that show where the plutonium and americium peaks probably are now. If for those of you who are accustomed to seeing alpha source spectra, the peaks might look a little bit wide to you. I want to remind you that this was done in air, so that there is a natural broadening to the peaks, and the sources were kind of distributed as well, so, which also gives a natural broadening to the energies that the alpha particles put out. And over the years, as we have been improving our silicon carbide linear energy transfers, we now have the spectrum that you see on the right, where you can definitely see the peak that stands out in the middle of the graph is definitely easily distinguishable from the background energy that's inherent in any system, which is that line that you see going up on the right. And now I'm going to talk about some of the envisioned applications. As John mentioned, CubeSats are a likely possibility. We were early contacted by a researcher who is studying radiation in the planetary environments and wanted to put a sensor on a CubeSat around a planet. And so we've worked with some folks on some proposals to do that. And this shows some of the concepts of what that might be like. The first picture shows the entire CFID sphere, how it might fit in a 6U CubeSat, and the picture on the right shows just some linear energy transfer stacks. We call them charged particle telescopes, which would then detect ions from space looking in different directions. And we have been funded by innovative research and development technology to improve those charged particle detectors, and so that is moving along. Another group that was interested in some of our work, the proposal was called SPAGHETTI, stands for Solar Proton Anisotropy and Galactic Cosmic Ray High Energy Transport Instrument. The PI, the science PI who was interested, that happened to be having spaghetti for lunch when he came up with the name. So, but he was interested in studying anisotropies in solar protons. And so we had a CubeSat concept to look at that. And this is more of a cutaway of how the linear energy transfer detectors, in this case, a two transfer detector stack called a charged particle telescope, would have been distributed around the CubeSat, and a cutaway of what the detector design was at the time. And this is more of the predictions of what we expected the spaghetti deep space CubeSat to be able to see, as far as the amount of directions. That the pink cones define the directions in which we expected to be able to receive data. Now, this was not funded. It was kind of a high-risk idea at the time because the concept would have involved putting propulsion on a CubeSat, which really had not been done very much prior to this. And some of the early propulsion CubeSat efforts that were funded at the time, ours was not funded, didn't go very well either. So it may not be that much of a setback that it wasn't funded. The other activity we're involved in, we have some external partners who are interested in using neutron spectra for lunar prospecting. So we're working with a company that develops neutron detectors. And instead of just taking the neutron energy, which typically is put into 3 bands of higher energy, medium energy, which is called fast, and then a low energy neutrons, which are called thermal. We want to try to essentially, when neutrons are liberated from, say, the lunar surface due to impact from cosmic rays, we want to be able to try to unfold the energy spectrum a little bit to learn more about what is in the lunar surface there. And so we have an effort to work with that group. And then we are also supporting surface fission power. One of the things we're concerned about is not only is your reactor a source of radiation, but it is in a radioactive environment, as has been discussed earlier. And one of the things we want to make sure is that, say, a environmental detector at some distance from the reactor doesn't misinterpret radiation from space as coming from the reactor and shut the reactor down when the reactor might actually be operating just fine. And so we are looking into using our CFIDS concept as an external environmental radiation monitor, and also developing some silicon carbide-based neutron monitors. One of the things that challenges that nuclear reactors have is that on Earth, the sensors that inform the control system are changed out on a schedule. And that schedule is far less than 10 years. And on the moon, we might not necessarily have spare sensors or people to change them out on a regular cadence. And so what we are trying to do with this research is try and examine the wide bandgap materials and choosing other materials appropriately so that we can see how long can we make those sensors that inform the control system for the reactor last, so that there is less that people have to do on the surface of the moon, and more that they can do more of the work they came to do, and less maintenance. And so that's really a summary of the work we're involved in. This actually started about 10 years ago or so. John and I and a colleague were not working in this area at all, and we started talking about the subject literally over lunch in one of the offices at work, and we started designing sensors at those lunches for a while, and then we started actually being able to do a little bit of work in this area. But we are working in trying to develop long-lived radiation sensors for a variety of applications.
questions?
Hearing none. Do you have everything else you wanted to cover?
No,
All right.
yeah, it's, yeah, if there was any questions, I mean, we're, like I said, we're working on these things in-house at NASA, in our clean room facilities, and, recently there's been a lot of interest, that we'd kind of attribute to the solar storm that we had not too long ago. But, yeah, we're really excited, applying this new technology to space science and space exploration.
All right. Big round of applause.
Hello, everyone. My name is Emily Brownie. I'm an undergraduate student at the University of Mount Union in Alliance, Ohio. I'm majoring in biomedical engineering, and I'm originally from Elport, Pennsylvania, which is basically just a rock's throw from the Ohio border. And I look forward to a career in the biomedical field and hopefully working with prosthetics. We're now going to take a break with snacks and beverages out there on the mezzanine. Please enjoy networking and build some new connections. And then in about 40 minutes, please come back for our next session, a Glenn Extra talk by Dawn Emerson about the Glenn Research Center Aerospace Communications Facility. Thank you.